The database batch job calculation is too slow and time-consuming. The time window is not enough, and the batch job cannot be finished during the night. There is no time to start over when a mistake is made. Being strained especially on critical summary dates, like end of the month or beginning of the year. What are the reasons behind these problems? The traditional framework for batch jobs is as follows. The data is exported from the production database, and then imported to the batch job database. After completing the calculation by writing stored procedures, the data is then exported out of the batch job database, and saved as files to other systems, or imported to other database. We all know that database I/O is very slow. The multiple exporting and importing operations during this process are the first reason for poor batch job performance. The second reason is poor performance of stored procedures. The SQL syntax system is outdated, lacking many data types and operations, which limits the implementation of efficient algorithms and results in poor stored procedure performance. Batch job often requires more than 10 or even dozens of SQL statements to be executed step by step. The intermediate results of each step need to be stored as a temporary table, and when the amount of data is large, it needs to be written to the hard disk, which can seriously slow down the entire stored procedure. For more complex calculations, it is also necessary to use database cursor to retrieve data in loop for calculation. But the performance of database cursor traversal is much worse than that of direct SQL, and it does not support multi-threaded parallelism, which will make the computational performance even worse.
Database is slow. Why is it still used for batch job?
This is because the calculation logic of batch job is quite complex, and usually can only be implemented using stored procedures of traditional databases. For general query scenarios, distributed databases can also be used to increase speed by adding cluster nodes. However, the stored procedure capability of distributed databases is generally weak, and some even do not support stored procedures, making it difficult to implement complex batch jobs, let alone improve performance. Since we can't find a better option at the moment, we can only use traditional databases to implement the batch jobs.
How about Java or Python?
It's still difficult to run faster either. Java, lack of structured data computing libraries, only has a small number of in-memory computing libraries, and almost doesn't have any of the high-performance algorithms commonly used in batch jobs on big data. It is difficult to implement them in Java itself, and the result is that application programmers often write inefficient code to avoid troubles. Moreover, Java does not have a universal high-performance storage, and implementing it by oneself is quite difficult. The performance of using databases or text files for storage is poor. Python has relatively rich computing libraries, but they are still only in-memory oriented. For big data that exceeds memory, hard coding is the only way, facing the same problem as Java, and the interpreted execution is slower than Java. Without a true parallel mechanism, it is difficult to fully utilize the computing power of multiple CPU cores. There is no universal high-performance storage, and it still requires the use of databases or text files, which is inefficient.
What else can we use?
SPL. SPL is a powerful tool for comprehensive acceleration in batch jobs. It can perfectly solve batch job performance issues. SPL provides low-complexity algorithms that can effectively reduce computational complexity and significantly improve computational speed. In many cases, it is impossible to write code of these algorithms in SQL, so it will be much slower. Many of these high-performance algorithms are originally invented in the industry, and the SPL code is also very simple to write. For example, batch jobs often require traversing big tables, or even many times, which can be very time-consuming. At this point, the multi-purpose traversal mechanism of SPL can be applied, and multiple calculations can be completed simultaneously by traversing the big table in one go, which can save a lot of time. The delayed cursor mechanism of SPL can implement stream computing and effectively reduce the number of intermediate results landing. SPL multi-cursor supports multi-threaded parallelism, fully utilizing multiple CPU cores to improve computational performance. SPL stores intermediate results that must be landed as built-in high-performance storage files, with much faster read and write speeds than databases. SPL can also directly calculate files, saving the time for importing and exporting in batch jobs. For example, SPL directly calculates the data files exported from the production database, avoiding the process of importing data into the batch processing database. SPL can also directly store batch job results in general formats such as text files, avoiding the exporting process of batch processing database. The results of batch jobs can also be directly accessed by other systems through JDBC or RESTful interface of SPL, avoiding the importing process of other systems. Take a look at the actual case of SPL accelerating batch computing tasks. A bank's corporate loan business batch job. The stored procedure has 48 steps and 3,300 lines. Historical data has 110 million rows, with a daily increase of 1.37 million rows. This batch job task involves complex multi-table associations, and the results of each step need to be stored as an intermediate table and written to the hard disk. Originally, the database took 115 minutes to run. When optimizing this batch job in SPL, the delayed cursor mechanism mentioned earlier was used to merge multiple steps into one, reducing a lot of time spent on writing hard disk and creating indexes. In addition, the application of high-performance algorithms such as multithreading parallelism using multiple cursors only took 10 minutes, resulting in a speed increase of more than 10 times. A certain spatiotemporal collision batch job aims to identify the top 20 mobile phones that have appeared the most frequently in the same time period and location as a specified phone, with a data size of approximately 25 billion rows. Writing SQL requires the distinct and join, which involve hash and comparison. When there is a large amount of data, the computational workload is also significant. A single node of a certain MPP database crashed directly, and it took more than 30 minutes for a cluster with 5 nodes to get the result. SPL sorts data by phone ID, gradually retrieves data of each phone into memory, and then performs complex conditional judgments. The calculation is finished in less than 6 minutes on a single machine. The star aggregation operation of the observatory calculates the distance between two celestial bodies based on their position, and then determines whether to establish an association relationship, which is a typical non-equivalence association. There are a total of 11 pieces of data, each with over 5 million physical records. Initially, 200 lines of Python code was written to implement this requirement, but due to Python's lack of support for multithreaded parallel computing and the lack of some native high-performance algorithms, such as binary search, it took 6.5 days to compute 500,000 celestial bodies despite a 10-fold reduction in the amount of celestial data. Switching to a distributed database, with the same 500,000 stars, it took 100 CPUs and 3.8 hours to complete the calculation. This is because databases can use the hash join method for equivalence joins, but for non-equivalence join, they can only traverse to calculate, which is very computationally intensive. After SPL was adopted, sorting the celestial data by their positions, then implementing high-performance algorithms such as binary search, and utilizing multi-threaded parallelism, SPL finished the calculation on the full 5 million data in only 3 hours, resulting in a performance improvement of 2,000 times. Moreover, SPL programming is much simpler than Python, and implementing this batch job only needs 50 lines of code. Implementing batch jobs in SPL can not only save the time for importing and exporting, but also replace stored procedures and SQL statements with higher performance algorithms. SPL is a powerful tool for comprehensively accelerating batch jobs.